Today's lesson is on operations with radical expressions. We talk about radicals. Radicals in this case in math mean anything with a root symbol. So radicals, roots, they mean the same thing. It could be square root, it could be cubed root, it could be any type of root that we're going to be looking at. A couple properties that we're going to use with radicals. One is called the product property. Product property says that if you have two different radicals, A and B, multiplied together, you can multiply those together and put them under one radical. Or you could do the other way. If you have a number under a radical, you can split it up into its factors into two separate radicals. For example, let's say you had square root of 16 x to the fourth. We can split that up. We could say it's the same as square root of 16 times square root x to the fourth. And then we could simplify each part to get the answer. Square root of 16 we know is 4. Square root of x to the fourth would be x squared, and we can get our solution. So that's product property. Another property that kind of goes along with that is called the quotient property. Remember, quotient means we are dividing. So if we have some type of root or radical over a fraction, that's the same as square root of the top, or the numerator, over the square root of the bottom, the denominator. Let's look at an example. Let's say we have square root of the fraction 36 over 7. Well, what that says we can do, what this property says we can do, is take square root of the top number over square root of the bottom number. Now we want to try to simplify each part. Well, the top we know, square root of 36, simplifies to 6. However, square root of 7, not a perfect square, doesn't quite simplify. Now, technically, that is the solution, but we never leave square roots in the denominator. So what we're going to be looking at, one of the things we're going to be looking at, how to simplify and get that square root symbol out of the denominator. And we've done this in the past. We did a little bit last try. What we want to do is multiply by whatever that square root in the denominator is, multiply by that square root to the denominator and also to the top, because if we are going to multiply by it, it needs to be equal to 1. Square root of 7 over square root of 7 is the same as 1. So if we multiply the top and bottom by that factor, we get 6 square roots of 7 over, now the bottom square root of 7 times square root of 7, be square root of 49, which equals 7. So we never want to leave radicals in the denominator. All right, so we'll be using those two. Just the reminders again, like we just talked about, when simplifying a radical, no radicals in the bottom of a fraction. So we don't want to leave any type of roots or radicals in the denominator. Also, no fractions underneath a radical. We don't, whatever's underneath a square root symbol or a root symbol or a radical symbol should only be numbers. We should never leave fractions there. All right. Now, to eliminate fractions, you can rationalize the denominator. So to eliminate fractions, we want to rationalize the denominator. What we're going to do, like we just saw in the last example, you want to multiply the numerator and denominator by a quantity so that the number underneath the radical is an exact root. Let's try this example right here. Square root of 9/5. Again, our quotient property we just looked at says that's the same as square root of 9 over square root of 5. Do either of these simplify? Yeah, the top does. Square root of 9 we know is 3. However, that denominator one doesn't quite simplify. We get to the same point. Don't want to leave a radical in the denominator. What could we multiply then to get rid of that? Multiply by that radical. So we want to multiply by square root of 5 over square root of 5. By doing that now, the bottom of our denominator, square root of 5 times square root of 5, square root of 25, which equals 5. On the top, we're left with 3 square roots of 5. There's our solution. Let's try another one. You have another example on your note sheet. Let's try this one. Cubed root of 2/9. Now this one's a cubed root. The last couple have been square roots. This one's a cubed root. Again, split it into its two parts. So we want a numerator, cubed root of 2, over the bottom, cubed root 9. All right, on this one, we got to look. Do either of those have a cubed root? Well, if you're not sure, cubed roots are kind of sometimes harder to think. If we don't use cubed roots as much as square roots, let's see if we can write out maybe a few cubed roots that will help us. We know 1 cubed equals 1, 2 cubed equals 8, 3 cubed, 3 times 3 times 3 would be 27, 4 cubed, 4 times 4 times 4 would be 64, and so on. Those might help us when we're simplifying cubed roots. Do we see either of those numbers with 2 and 9? Nope. So neither of them are perfect cubes, but we don't want to leave that cubed root of 9 in the denominator. So we got to find something we can multiply by to eliminate that. So we need to multiply by some cubed root. Now if we multiply by cubed root of 9, it's not going to work because cubed root of 9 times cubed root of 9 would be cubed root of 81, and 81 is not a perfect cube. So we want to look over here at our list. Do we see a perfect cube or something we could multiply 9 by to get a perfect cube? And this one, 27, is a perfect cube. So we know 9 times 3 would be 27. So let's multiply by cubed root of 3 over cubed root of 3. If we do that, now on top we got cubed root of 6. On bottom we have cubed root of 27. And cubed root of 27, looking over there, we see is equal to 3. So our answer would be cubed root of 6 over 3. Now we no longer have the radical in the denominator. Cubed root ones are a little bit harder than the square root ones, just because we don't work with them as often. All right, let's do some other examples. Now we're going to just simplify. We're going to go through simplify different types of radicals. Some of them have just numbers. Other ones will have both numbers and variables. First problem, only a number. Square root 198. So what we want to do is look for, is there any perfect squares we can pull out of 198? It might help again if you list out perfect squares. We know 1 is a perfect square. 1 times 1 or 1 squared is 1. 2 squared is 4. 3 squared, 9. 4 squared, 16. 25. 36. 49. All these numbers are perfect squares. All right, so we want to look, are any of these, and there's more, are any of those perfect square numbers in 198? Well, 198, not a number, again, we use very often. Maybe try dividing it. What goes into 198? And try some of those perfect squares. If you try 198 divided by 4, so let's bring up our calculator. If we divide that by 4, we get not a whole number. So 4 didn't work. So let's try another one. Let's do 198 divided by 9. 198 divided by 9, that works. If you divide 198 by 9, 9 times the quantity 22 equals 198. All right, so when square root of 9, we brought that out. 22, is there any other perfect squares in 22? No, the only numbers that go into 22 are 2 and 11. So this one would equal, because we know square root of 9 is 3, 3 square roots of 22. Let's try another example. 3 square roots of 54. Now you can already see there's a number 3 that's been pulled out of this radical. We want to see, is there any other ones that can get pulled out? So looking at the number 54, is there any perfect squares that go in there? Again, try dividing, see if there is. If you try taking out 9, 9 does go into 54. So square root of 9 times square root of 6. 9 times 6 equals 54. Square root of 9 again is 3. So we got 3 times another 3 now, times square root of 6. Simplifying, 9 times 9 is, or 3 times 3, I'm sorry, is 9. So 9 square roots of 6. And that's our solution. So when it's just numbers, look for perfect squares that go into whatever your number is. All right, number 3. Now you start seeing some variables involved. Now we got some variables. So with the variables, start with number. Get the number part done first, then look at variables. Try to simplify those, just like we did the other day. All right, let's try 190. The number 128. Do we have anything that goes into 128? Well, 128, again, bigger number. You know it's even. Maybe try dividing it, but any even number we know divides by 2. So if we take 128 divided by 2, it breaks up into 2 and 64. Is 64 a perfect square? Absolutely it is. So we can say this is square root of 64, square root of 2. All right, we also got our variables here. We got square root of x to the 4th, and we also have square root y cubed. Now we got to try to pull out any perfect squares. Square root of 64 is 8. Square root of 2, not going to simplify. We'll leave that under the radical. Square root of x to the 4th. How many times would x go in there? We'd end up with x squared. All right. Square root of y cubed. Is there any perfect squares we can pull out of there? Yeah, one perfect square. We can think of that as square root of y squared times square root of another y. Square root of y squared would be a single y. So the final answer, square root x squared, this part would equal a y, square root of y. The final thing you want to do, if there's any radicals, you want to put them all together into one final radical. So our answer would be 8x squared y, and then we'd have square root of 2y left over. There's our solution. All right, number 4. Now we start getting into a little bit of multiplying with radicals. Recall before our product property with radicals said if you have two radicals being multiplied together, that's where you want to start. Multiply them together, combine them together, see what you got. So let's multiply these together. We got the numbers 24 and 12. If we multiply those together, that gives us 288. All right, now let's multiply our x's. We got x to the 6th in the first term, x in the second term, that'd be x to the 7th. And do the same with the y's. Y cubed and y would be y to the 4th. Now again, we want to try to simplify. 288, it's an even number, means it divides by 2. 2 and 144. Is 144 a perfect square? Yes, it is. Yes, it is. So we got square root of 144 times square root of 2, x to the 7th. When it's odd like this, not all the x's are going to come out of the radical, but we know 6 of them will, so we could split that up into x to the 6th with another leftover x. And then finally we got y4. All right, let's simplify now. Square root of 144 would be 12. Radical 2 we got to leave. Square root x to the 6th would be x cubed. This x we can't really do anything with. And square root of y to the 4th would be y squared. Now we write any remaining radicals into the same one. So we'd end up with 12 x cubed y squared times radical 2x.